Before we begin the interview, I wanted to briefly introduce myself. My name is Latif, and I'm a research assistant at Wayne State University studying neuroscience. Today, Tuhfatul and I will be interviewing Dr. Aina Puce. Dr. Puce is the Eleanor Cox Riggs Professor in the Department of Psychological and Brain Sciences at Indiana University in Bloomington, Indiana, USA. Currently, she is a senior editor of the journal Neuroimage. Her research expertise includes human brain mapping using EEG and MEG. Thank you so much for joining us today, Dr. Puce.
Thank you, Sana, and thank you, Tuhfatul and Aishi, for inviting me to speak with you today. I appreciate it.
As Sana introduced herself, my name is Tuhfatul Tasnim. I'm also a research assistant at Wayne State University, and I'm also majoring in neuroscience with a minor in biological sciences. And so jumping right into the interview, we wanted to talk about your publication titled IFCN Endorsed Practical Guidelines for Clinical Magnetoencephalography, also known as MEG. It was authored by Rita Hari, Aina Puce, and others. Now, would you please tell us a bit about the significance of the guidelines of the use of MEG?
Yes, well, before I actually deal with that particular paper, just to give you a bit of a background context of that paper was work that was commissioned by the International Federation for Clinical Neurophysiology, and it does a very important job of periodically providing guidelines for best practices for many aspects of EEG in particular, and this was an attempt to do that for MEG. It was a committee of experts, mainly in MEG, led by Rita Hari at the request of the executive of the IFCN. Rita Hari invited a whole lot of very learned MEG experts to the table, and I am the only EEG expert on that committee. So that was how my role was on that committee, and we have many authors. There are, I think, 16 authors, if I recall correctly, on that paper. And so my role was fairly minimal. I helped where I could. I read for coherence. I put suggestions forward, but the main work was done by Rita and all of the MEG experts. So that's the background context to that paper. The paper is focused on trying to generate a set of clinical guidelines so that people who are doing clinical MEG studies can use best practices and use common best practices that are known around the world that a group of experts has agreed on. So that's really the purpose of the document. And it's hard to get consensus because many people have good reasons for doing things the way they do, and it includes the kinds of tests they do and the way they record activity using different stimulation devices if they're doing evoked activity. But so this was a set of guidelines that we tried to implement that provide a consensus of what best practice might be, and that might be helpful to people who are getting into MEG in the clinic for the first time, as well as those who are actually using it as well. So that's the story with that.
Thank you so much.
Yeah, thank you for giving us that background into your paper and for kind of discussing how clinical guidelines are important, and especially the ones that you developed with your team with Rita Hari. I wanted to bring attention to your paper, Magnetoencephalographic Study of Occipitotemporal Activity Elicited by Viewing Mouth Movements. Would you please tell us about the rationale of human brain mapping with EEG and MEG?
Yeah, it's we're trying to, with MEG and EEG, we're trying to understand the timing of the neural activity and how our brain activity influences behavior, whether it's sensory perception, decision making, attention, and so on. And so EEG and MEG give us a really good handle on that. It's a bit harder to work out where things are coming from inside the brain, although it's possible with source modeling, and particularly with MEG. And there are other methods like a functional MRI that are very useful for working out where the activity is in the brain, but they're pretty bad at the temporal side of things, the timing. So EEG and MEG are wonderful at the timing. There are differences between EEG and MEG, even though they're measuring neural activity. And the differences in them come about because of the sensitivity of the measurement sensors for each method. And for MEG, the magnetometers and radiometers have a sensitivity to magnetic fields outside the head. The geometry of the brain and the anatomy dictates that how the magnetic fields that emanate outside the head are actually measured. And so what happens is, if you have brain activity that's in the folds of the cortex, then you're going to have currents in the folds of the cortex that go parallel to the surface of the scalp. And in doing so, you're going to have lovely magnetic fields that can be detected outside the head. If, in contrast, you have activity on the surface of the cortex, on a gyrus, the neurons are lined up, and the main current is going to be pointing perpendicular to the surface of the scalp. The magnetic fields that are associated with that are going to go around that set of neurons in a circular fashion and not leave the head. So MEG samples activity mainly from the tangential sources, the sources in the sulci in the head. It's also wonderful because it doesn't distort activity. Magnetic fields pass through tissue like the skull and the scalp, and they don't get distorted. So the activity is remains fairly undistorted, and it's well seen on the head for the fields that can be measured. Contrast that to EEG. EEG is can be seen from sulci and gyri, and it's really, really complicated in the way that the activity of neurons, the slow activity that's generated from postsynaptic potentials, comes together. And it can come from sulci, it can come from gyri, and if the signal strength is big enough. And that makes modeling and working out where that activity is coming from in the head really difficult. What's also difficult with EEG is that the electrical activity gets distorted as it passes through tissues like the skull and the scalp. And so by the time it gets to the surface where you're measuring with the detectors, you end up with a signal that's smeared. It's a bit larger in distribution than MEG. So there are differences between the two signals. But the one interesting and cool thing is that when you look at the MEG topography and EEG topography, the patterns are 90 degrees apart if you do the recording, say, simultaneously. And that's really, really, it's a nice sort of sanity check, if you will. But they're the essential differences between the two. But we need both, in my opinion. We need both because MEG is an expensive, well, it has been an expensive technology because it requires supercooled sensors and a magnetically shielded room. EEG doesn't need that so much. EEG can be performed in a regular room, doesn't need supercooled sensors. It's much more economical and accessible to labs. So that's why we need both, because they serve slightly different purposes.
All right, thank you so much for your insight on that and your very thorough explanation of EEG and MEG. I definitely think I understand it much better now. Moving on to the career development portion of this interview. Now, I wanted to ask you about what your motivation and what really drove you to pursue a career as a neuroscientist.
Yeah, it's interesting. I always like to listen to other people's stories about how they got to where they are. And the one thing that always strikes me is that those journeys are never straight. They always take turns and they meander and all of that. And mine was the same. I've always been fascinated in doing science ever since I was a child, and I used to do experiments outside in the garden using earthworms and other creatures that my mother wouldn't allow into the house because she didn't like them. And we lived in Australia, so some of those creatures were pretty scary and big. But I went through school always enjoying science and ended up doing a biophysics and instrumental science degree, a dual major as an undergraduate. And then decided maybe I need to get a master's degree because I probably need to have an edge and get a better job than some of these other people that are also looking for jobs. I wasn't really thinking about a career in research at the time. I did my master's degree and thought, this is kind of a good thing to do. I kind of like doing this. So then I signed on to a PhD, and I had two opportunities to do a PhD in Australia in two departments, and I chose one of them, and that was at the University of Melbourne. It was in a teaching hospital in the neurology department, where I tested and did intracranial EEG recordings in epilepsy surgery patients. So that was in a neurology department. I also did clinical testing of patients. That was how I earned and paid my rent. That really started it all off. And I was interested in brain function. I was interested in getting access to the brain directly, which of course you can do with intracranial recordings. And then there was the other added bonus was that I could actually hopefully do something to help these patients with their diagnosis, for the seizure diagnosis as well. So that was that. Then after that, I did a postdoc, trying to move on from that work. And I wanted to go overseas, so I came to the USA and to a lab that I had greatly admired, to the lab of Truett Allison and Greg McCarthy, who were also doing intracranial recordings at Yale. And this was in the Department of Neurosurgery now. And they were also starting to do functional neuroimaging as well. They were doing scalp EEG, and they started functional MRI. And this was in the early 90s. And that was when we started. We were probably one of 5 labs in the world. The first paper in the lab came out in 1993. It was work that I did not participate in because I hadn't been in the lab yet. But everything else after that I participated in, and it was an amazing opportunity to work with a new technology. Never abandoned EEG, but always have used both since that time. After the postdoc, that was in the neurosurgery department at Yale, I went back to Australia to try and start my own lab in the Brain Sciences Institute at Swinburne University of Technology. And I took on eventually a assistant directorship there. And then I moved back to the US. Why did I do that? Because I had a dual career problem. And that's what happens when you marry another neuroscientist. This is career advice to people. Don't marry another neuroscientist if you're a neuroscientist. So I'm back here in the US, and I've stayed here ever since. I went to a radiology department after that at West Virginia University and ran a research imaging facility, which was co-shared with the clinical unit. And then now I'm at Indiana University in psychological and brain sciences, where I originally came here to run their imaging centre. I don't do that now. I can actually concentrate on science and teaching. So that's my journey. And you see, it's taken a neurology department, a neurosurgery department, radiology. Now it's psychological and brain sciences, and it all started in a physics department.
Thank you so much for sharing your journey with us. I mean, that Tuhfatul can agree. That was definitely really interesting. And kind of on that same topic, I was wondering what kind of advice you would give young students like Tuhfatul and I that are interested in pursuing neuroscience in the future.
Yeah, if you had have asked me that a year ago, I probably would have said something different. I think getting to know as many people as you can in the area, reading widely, making contacts, opens up opportunities that you may not expect that might happen later in life. I think talking to people, asking people, emailing people. It's hard to make contacts at conferences right now, but we're trying to do things virtually. If and when we do go back face to face, if you are in a lab, having your advisors pay for, you know, those conference visits. And I think probably the main and the most important thing is to pursue something that you're passionate about. Because if you're not, when times get hard, then you're going to lose interest and you're probably not going to succeed. Even if you're passionate about something, it's very, very hard to succeed. Because when you're doing science, you learn from your mistakes and you make a lot of them. And I think the further you go in science, people talk about your successes and what you've done. But honestly, I've built my career on mistakes. And that's why I am where I am now. And so that's I think a lot of people who are doing science, who are starting out in science, get frustrated by the failure because you'll fail and you'll always feel like you don't know something. I'm learning right now. My lab has switched to Python. Okay, we've jumped off the cliff. I'm learning Python. My new graduate student is further ahead than I am on it. She's great and she's motivating me. It never stops. And if you're not prepared to always feel stupid, always feel like you don't know something, this is probably not the career for you.
For sure. That was also very motivational, I'd just like to say. I had a question kind of for our undergraduate students who move overseas. Like you said, you moved from Australia to the United States to study. Now, can you talk a little bit about how you adapted and what challenges you faced and how you overcame them?
Yeah, that's a really interesting question. And it's something we talk about a lot at our university, because a lot of our students come from, our graduate students now, not just undergrads, but undergrads, graduate students come from other countries and they have to adapt. And for me, as an Australian, you'd think coming to America would be easy because we speak English. But it becomes pretty apparent after a while that you're speaking a different English to those other people. And it can be a tremendous source for confusion. And so I learned that. I learned not to use idioms and expressions that nobody understood. It took me about 3 years to understand the sense of humour because it's very different culturally. And it took me, about 3 years before I could tell a joke. And that was really weird. I can imagine what it's like for people who come whose English isn't their first language. I just spent 2 years ago, 6 months in France, in Paris on a sabbatical, living and working. And my French is passable, but I wouldn't say I was at all fluent. And it's hard. It's hard when you go to a lecture and you have to take notes. It's hard when you go to a conference and it's all not in English. You just have to persist, but it's really tiring when you're working in a language that's not something that you're a native speaker, and it's very, very tiring. So that's a tricky thing. And then there's the cultural adjustment. Of course, people either will accept you or they won't. And unfortunately, in many parts of the world right now, there are many places that are not as accepting of people from many locations in the world as they should be. And so that's creating a few problems for people. We have a lot of international students, undergraduates and graduate students at Indiana University, and our university is trying to do what it can to make them feel welcome and feel like they belong, which they do. They're part of our university. So this is a difficult time, and we all need to support people who come from other countries and make sure they're okay and check in with them. And that's what we do as faculty with our students. We check in with them and see that they're okay. For students also, it's hard to do research now. I have an undergraduate student who's been in my lab now for a number of years. He's graduating next year. He's doing an honours thesis. We're going to use old data that he helped collect. We have the data, but we can't collect data right now. My lab is closed. So fortunately for him, we have a plan for him. So it's a tricky time right now. And changing cultures is tricky. I think the advice would be open to what other people offer you, because I've learned living alone in other cultures how enriching that experience can be. So that would be the positive side that I would leave you with there.
Thank you so much for letting us know about your personal experience coming from Australia to here, and really about like the importance of supporting students that come from abroad, and how we really need to begin to embrace more cultures, especially here in our schooling systems. Do you have anything else that you'd like to say to the audience before we wrap the interview up?
Not particularly. I think that the only thing advice I'd give to people now would be just we need to stay positive. We need to all work together in our neurophysiological world, because it is a world. And I'm grateful for my collaborators in other countries that I interact with, and I interact with every week. And we need to keep in touch and remain and keep our ability to work together, because that's how we're going to create better science and move things forward and try and understand what's under the hood here. And that's really the name of the game, whether the brain is working well and it's healthy, or if there is disease. We need to get to the bottom of it. And the only way we can do it is by working together without borders across the world.
Again, we'd just like to thank you again so much for sitting down and doing this interview with us and sharing your insight and your experiences. I think it'll be very beneficial for other undergrad students, because I learned a lot, and I'm sure Sana did as well. And we will continue reaching out to other neuroscientists and clinicians like yourself to learn more and just spread the word.
Thank you very much for your time today. It's been an absolute pleasure.
Thank you so much. This was an amazing experience.
That's good. The other thing is the other thing that you may want to investigate too, if you guys are going to do a lot of this, maybe look at some stuff on media training and things like that. That could be very helpful to you too. Might make you did a beautiful job, but it might make you feel more comfortable, because I bet you weren't comfortable doing that, right? you looked comfortable, but probably inside you weren't. And that might help too. I've done media training, and boy, it really helps. I did a couple of programs through my universities that had journalists come in, and they were running, or they were former journalists, and they had run a program, and then they would interview you and tell you what you did wrong and give you a strategy of how to be interviewed. That was for newspapers, for radio, for live radio. That's really scary when you do live radio, and then television as well.